Hello, everybody, and welcome to the second day of INSPYRE 2022, the International School on Modern Physics and Research organized by the Frascati National Laboratory of INFN, Italian National Institute for Nuclear Physics, and addressed to high school students attending their last 2 years. I am Susanna Bertelli, technologist at Frascati National Laboratory, and I will be your virtual host for today's lectures. The first webinar is devoted to dark matter and is held by Professor Laura Baudis. Laura Baudis is a full professor in experimental physics at the physics department of the University of Zurich. Among her research fields, there are dark matter, the fundamental properties of neutrinos, and particle detection techniques. I remind you that you can write your questions in the chat, and at the end we will answer to a few of them. Professor Baudis, the floor is yours.
Thank you very much for the kind introduction and also for the opportunity to be here. So today I'll bring you on a tour on dark matter, direct dark matter searches that are conducted, as we shall see, in deep underground laboratories. But first, let's see a little bit what we know or don't know about dark matter. So imagine that you look at the sky you're high up on a mountain and you look at the sky in a very dark, clear night, and then you will see, when you're lucky, you see thousands of glimmering light sources and perhaps even this extended nebulous band of the Milky Way. And today we know that this band, the Milky Way, is made of 100 billions of stars, and that's our home galaxy. However, we are part of this galaxy, so we cannot really see it from the outside. But if we could, then it would look very much like our close neighbor, another large spiral galaxy, that is Andromeda. And Andromeda is about 2 million light years away. And because kilometers is not a good measure of distance on cosmic scales, we use these light years. So basically, 1 light year is the distance that light travels in 1 year. So it's about 9.5 of trillions of kilometers. Yes, and we are, if we would imagine this is now the Milky Way, we are a bit at the outskirts of the Milky Way, and we are moving together with the solar system, together with the sun. We are moving with about 220 kilometers per second around our galactic center. Now, if we move from galaxies to, even if we zoom out, right, and we move to larger distances, for instance, here to about 1 million light diameters, then we see here one large so-called cluster of galaxies. So these are, thousands of galaxies that are held together by the force of gravity. And this particular cluster, we will discuss a bit later, is called Coma cluster. So that's around at a distance of 300 million light years from the solar system. Now, today we can make many, many beautiful pictures of the universe, of our cosmos, but not only in the visible range, what I've showed so far, but we can map this so-called visible universe in many different wavelengths with all kinds of different telescopes, namely from probably you have heard, from radio waves to microwave, infrared, and then this visible, what we can see with the naked eye, all the way to these very high energy gamma rays. And this allows us to have a much more complete picture of our universe and, to understand many of these astrophysical phenomena that we observe. However, what we see with this is all electromagnetic radiation. So what we see with these telescopes that detect electromagnetic radiation in different wavelengths, this is what we call visible matter, right? So now the question is visible matter really the dominant form of matter in the universe? And you probably already guessed the answer if I ask the question. But we will discuss a few of these observations, but just to give you now the big picture, we know from many, many observations over the last decades that, in fact, most of the matter that we have in the universe is not visible. In fact, 85% is non-luminous or dark. As we shall see, that simply means that it does not interact with light, with electromagnetic radiation in any wavelength, right? And we know this from observations of galaxies, of clusters of galaxies, these are even larger scales. We call them large-scale structure of the universe. So everything that is larger actually then such a galaxy cluster, and each dot here in this picture, so these are observations, these are here simulations of these large-scale structures, every dot is one galaxy. And even from this cosmic microwave background, that is the radiation that was emitted when the universe became transparent about 400,000 years after Big Bang, and then reaches us today in terms of in this microwave wavelengths. So from all of these observations, we know that actually most of the universe is dark. But let's move back a little to the beginnings. So this all started not quite 100 years ago, but almost, with this Swiss American astronomer Fritz Zwicky. He was at Caltech back then, and then he studied in detail the motion of individual galaxies here in this large cluster of galaxies that's called the Coma cluster. And what he observed is that these galaxies, that the speeds were way too high. So actually all of these galaxies should actually fly apart if there would only be this luminous, this visible matter. That is also these galaxies, but actually also the gas in between. So back then he postulated that there must be some other form of matter. So he wrote this paper in German. He called it dunkle Materie, dark matter, that like sort of a glue keeps all of these galaxies in the cluster together and prevents them from flying apart. So these observations then, went unnoticed for quite some time. But then in the 70s, there were other observations. Now we move back from the scales of these galaxy clusters to the scales of galaxies. So there was Vera Rubin and her team and others that now study the motion of stars and gas in this spiral galaxy. So they measured these rotational speeds when you go from the center to outwards, and this is what you would expect here if this rotation would be due to visible matter alone. And this is mostly what they measured. So this was quite consistent actually with this hypothesis by Zwicky that there must be much more matter in these galaxies that what we can directly see than luminous matter alone, to keep actually the stars and the gas from flying apart. Even our own sun, would not be stable in its orbit. So and in the meantime, this was in the 70s. Now we have this what we call galaxy rotation curves from many thousands and thousands of galaxies. We have all these other studies that tell us that actually dark matter forms all the structures that we observe in the universe today, in particular also galaxies. And we know that it's there, even we can't see it directly, because of its gravitational pull, so gravitational force on the stuff that we can see, right? On gas, on stars, galaxies, and so on. And in spite of the fact that we have all of these studies, we still need to answer, the most fundamental question almost, namely, what is this dark matter made of? So this is something that we really do not yet know. We have theories, we have hypotheses, but we don't know the answer. Now, we have to go back a little and just remind ourselves, okay, what is normal, what we call normal or luminous matter made of? And you probably all know that normal matter, is made of, of molecules, of atoms. Then atoms, they have these atomic nuclei that are made of neutrons and protons, and then these clouds of electrons surrounding them. Then you may have also learned already that neutrons and protons are made of quarks. And in fact, you see here this nice chart of all the so-called elementary particles. So we think that these particles, at least as far as we can measure, they are elementary. So we call them also point-like. They are not made of other particles, right? So we have these quarks, and then what we call the leptons. So these are the electrons, and the heavier siblings, these are the neutrinos. And then these are the so-called force carrier. You probably already know the photon, and finally also the Higgs boson. So we know about all of these elementary particles. We have discovered, measured them, and so on. But we also know that none of them can be the dark matter. Actually, neutrinos here are the only particles, they don't interact with photons. But on the other hand, we know that neutrinos are way too light. We don't know their mass. This is what the actual mass is. This is another topic of actual research. but we know for sure that neutrinos cannot make the dark matter in the universe. Now, we also know that all of these elementary particles, they were made in a very early stage of the universe, and these are even though they are very early times, these correspond to energies that today we can probe in accelerators. So it's well studied physics. And what physicists believe is that together with these known particles like quarks and antiquarks, electrons, and all of their antiparticles, there were also other particles that could have been produced, so-called dark matter particles, that, however, we haven't detected so far because they interact very, very feebly, very weakly with our normal, standard particles, the ones that we know. So first, let's see what do we actually know about these dark matter particles, right? So it's a hypothesis that probably they could have been produced with these other particles in the early universe. So we don't know much about them, but from these astrophysical measurements and also from the fact that we haven't found them so far, we know that they don't have any electric charge, they don't have a strong interaction like quarks, for instance, and they're also slow moving. Slow moving means that they had non-relativistic or slow velocities when these structures in the universe formed. And we know this because we can simulate in computers what do these large-scale structures that I mentioned look like if these particles are cold or slow or a bit faster or really fast, and this would be the case here for neutrinos. And these simulations, we can then compare them with observation, and it looks like the dark matter has to be, these particles have to be cold, so slow moving. And of course, also, if they have to make the dark matter today, they have to be either stable, they should not decay to other particles, or they should be very long-lived, so much longer than the age of our universe, because otherwise they wouldn't be there today to make this dark matter. And there are quite a few candidates, possible candidates for these dark matter particles. And one of the leading hypotheses for cold dark matter is so-called weakly interacting massive particles, or WIMPs. Weakly interacting means the probability they would interact with the particles that we know, with quarks and leptons and so on, is very, very small. Thermal relic means they could have been produced in this very hot early phase of our universe when we know we can calculate and measure that all the other particles were produced, and we can also then calculate the density of these particles today, if they exist. And interestingly, when we do this, it actually matches very well the observations that we have from astrophysics about what is the density of this dark matter in the universe. And we will come back to this a bit later. So this is one of the leading hypotheses. And if these particles really make up this halo of galaxies and our own Milky Way, then this is what it would look like. So the idea is that what we see, these visible parts of galaxies are embedded in much larger halos, as we call them, of this dark matter, or invisible particles. Invisible, as I said, for electromagnetic radiation. However, they interact via gravity, so they have this gravitational influence on the luminous matter. And this is a computer simulation. Now, so this is what we said. Okay, the dark matter could be a new particle which does not emit nor absorb any light, right? So does not interact with electromagnetic radiation. But then the question is, how is it possible to actually make this particle visible? How is it possible to look for them? There are various ways, and the one that we will discuss here is the so-called direct detection. Namely, here we look for very rare collisions of these unknown particles with atomic nuclei. So you can imagine like a game, with a billiard game. So such an invisible particle comes, but it has a mass and it has a kinetic energy, and it would just collide with a nucleus and then impart some of its energy onto this nucleus, or perhaps even on the electrons in these atomic shells, and then we can detect the energy that is deposited either by the nucleus or by these electrons when they move through the material and lose this energy. So Just one formula here very briefly. Now, in order to build detectors to look for dark matter particles, we need to know what to expect. So basically, I will show you later, we measure a so-called recoil spectrum. So assume this is what we measure in a detector on Earth, or even better below ground. And then we need to know the number of nuclei, atomic nuclei that we have in the detector that we can calculate when we know the mass. But we also need some quantities from astrophysics. We need to know the density of dark matter, not in general in the universe, but here in the Milky Way, and even better at the location of the solar system. They will move with a certain velocities, actually not a fixed velocity, but a certain velocity distribution. This is also something that we need to know. And we also need to know what is their mass and what is their, what we call in physics, interaction cross-section, that is proportional to the probability that they will scatter on this electron or on the nucleus, okay? And then we need to know some detector physics. So it's a bit of an interdisciplinary field. We need to have all of these inputs to predict what we would see in a given experiment. Now, the flux of dark matter particles, this is actually known from the measured so-called rotation curve of our Milky Way. And here we measure the local dark matter density. So the local dark matter density is this quantity here, okay? And you can imagine that since we, together with the sun, we move around this galactic center, we will see these particles coming onto us with a given velocity. And we can actually calculate this flux when we assume a certain mass. So for example, for dark matter particles that are about 100 times heavier than the mass of a proton or a hydrogen atom, we expect about 10 millions of these particles through our hand for every second. So this seems like a large number, but it's actually not that large. And also the problem that I mentioned is that they interact just very rarely with normal matter. And there's even another problem. We have this constant background. So on Earth, we are constantly bombarded by what we call cosmic rays. So these are from primary cosmic rays. These are mostly high energy protons. So the high energy nuclei of hydrogen atoms, they come onto the atmosphere, they collide here with molecules, with atoms in the atmosphere, and they create these showers of particles. Also electrons, gammas, and neutrons, protons, and so on. And these would then interact with your detector and give you much higher interaction rates or much higher signals than what you expect from these dark matter particles. So it's really impossible to place a detector on Earth. And because of this, we need to place them deep underground. So to shield. So we use the Earth basically as a filter for these cosmic rays. And one of the, I would say maybe the most well-known and famous underground laboratory in the world is the Gran Sasso laboratory in Italy, that is in this highway tunnel that connects L'Aquila with Teramo. And it's under about 1,400 meters of rock. So this we use as a shield against these cosmic ray particles. And there are a lot of experiments in this lab, and also quite a few experiments looking for dark matter, and also some neutrino experiments. But this is not, of course, the only underground laboratory. There's quite a network of them in several countries, also in several continents. All of these laboratories also host experiments to search for dark matter. So there's quite a race. And depending then on the type of your signal that you're looking for, we have many different experiments. And we will learn today about one kind. But yes, because it would be quite a lot to talk about all of them. But I just want to mention that some of these experiments look for the small light or scintillation signal when particles scatter in the detector. Other experiments look for a tiny charge signal or ionization, while other experiments look for heat or, these are lattice excitations if you have a crystal, or so-called phonons. And depending on the type of experiment, on the material, you can look, for charge, but also charge and light, or light and heat, And many of these experiments look for two signals at the same time, because that will, in addition, gives you some handle to distinguish a signal from a background. And we will see what the background is. Apart from these cosmic rays, we can still have many other sources of backgrounds, unfortunately. But just to recapitulate, what is the main challenge to look for these dark matter particles? So we can calculate the expected signal, and that is unfortunately very small. And that comes from the fact that they are relatively slow moving. We said these are cold dark matter, so they don't have very large velocities, at least compared to the velocity of light. Also, we know that these interactions, these collisions that we are looking for are very rare, also from the fact that we have actually seen any so far. So about smaller than one event per a ton of detector material and per year, right? So if you only have 1 ton of a detector, you probably need to wait several years, right? So in the end, you have to build larger detectors. And even though you go deep underground, they can be, if this is your signal here, you can have a background that is millions of times larger. So we will see what we can do about this background. But first, you may ask yourself, okay, we have all of this background, maybe we can reduce it. But if we see a few signals, let's say 10 per year, how can we know that this is really from dark matter, and not some new source of background that we didn't think about so far? And that's always possible. However, we can also predict some of so-called signatures that have to come from a dark matter particle. So first of all, this is something that we can measure, this rate, and this depends on the dark matter particle mass, but it also depends on the target material. So whether you use silicon or germanium or xenon or argon, the spectrum will look a bit different. So you want to employ different detectors to see the different signatures. And some strong signatures come from the fact that I mentioned that we move together with the sun around the galactic center, and the Earth actually moves, of course, also around the sun. So we will see in the summer, these particles come onto us with a bit higher velocities than in winter. And this is why we expect such an annual modulation, a small change in rate with the seasons of our dark matter signal. And also we expect a change in the direction just because the Earth spins around its axis. So we have some handles once we see some signals to check whether this is really dark matter or maybe some new source of background. And today I will discuss detectors using xenon, and basically mostly xenon in its liquid form. So these are now the largest, some of the largest detectors that exist, and also they have a very high sensitivity to these dark matter particles. So I will show you how the detectors look like, but this is here the principle. So you have a large volume of liquid xenon, and on top of it is a gaseous phase of xenon. And you have two arrays of photosensors, one that's in the liquid and one that's on the top in the gas phase. So now let's say a particle, it can be, of course, in principle, we want to see dark matter particles, but it can be normal particles that we know, gamma ray or a neutron or electron. So they come in, they interact, and they make a first light signal, scintillation light. And this is in the so-called VUV, so it's UV light, around 175 nanometer wavelength. And we call this signal S1. At the same time, such an interaction not only creates light, but also a few electrons. And if you apply a drift field in your detector, for instance, here between we have here a cathode and then a gate and then the anode. So you have an electric field, and these electrons move upwards towards the anode. But first, then we extract them into the gas phase, and here they will collide with more xenon atoms and produce what we call a secondary or proportional light signal, and that's what we call S2. So these two signals will give us quite a lot of information: the energy of the interaction, the position in 3 dimensions, and as I will show you, the ratio of the two can also tell us whether it's more a background kind of event or something that like a nuclear recoil that we expect from a signal. And in this case, one of the first examples that I will show you, we had a 3.2 tons of xenon around xenon is liquid around minus 100 Celsius. But if you look now at the charge signal, so the charge is these electrons that we then in the end also detect as light here in these photosensors. If you look at the charge versus this primary light, then we have these two distributions that we can distinguish. The so-called background light that come from electrons, from gammas, or from signal light that we here simulated with fast neutrons that also create these nuclear recoils. And the second example that I will mention, a second phase, will have 8.6 tons then of liquid xenon, as we shall see. But here a little bit about the history. So these are experiments at the Gran Sasso Underground Laboratory. We started quite some years ago with a smaller experiment that was called Xenon 10. So that was 15 times 15 centimeters, only 15 kilograms of liquid xenon in total. Then we had a Xenon 100 detector that was roughly 30 centimeters diameter, 30 centimeters deep. Then I will discuss here Xenon 1 ton that was much larger, 1 meter diameter, 1 meter high, and currently we are running this detector, about 8.6 tons of xenon in total, so 1.3 times about 1.5 meter, and at the same time we are doing preparations, research and development then for the next phase that will have 50 tons of liquid xenon in total. And you shouldn't worry too much about these numbers. So this just tells us what is the cross-section that we can probe or that we could probe, so the interaction probabilities. And what this tells you is that with each experiment, you want to improve, 1 or 2 orders of magnitude in terms of your sensitivity to dark matter interactions. Okay, so yes, so we go to larger and larger detectors, but this only makes sense if at the same time we can also reduce the background, because actually this background, scales with the mass if you don't do anything. So yes, you will have an increase in sensitivity, but it will not be here a factor of 100 or a factor of 10. So with each scaling, apart from all the technological challenges that come with making this detector larger, making them work, there's a big challenge on how to reduce also the backgrounds, always at least by a factor of 10. And there are different ways of doing this. And yes, we have to actually use all of them. So just as an example here, for Xenon 10, you see here the outer part, the so-called cryostat, that helps us to keep this xenon liquefied and cold. We still had a lot of cabling. We had these traditional shields that is made of lead and poly, so lead to shield the gammas coming from the laboratory walls, and this polyethylene to shield against the neutrons. So even when you're deep underground, you still have the radioactivity of all of your materials. We will come to the detector materials, but also of the lab, of the walls, of the other components. So we have this natural reactivity, uranium chain decay, thorium chain decays, and others that then emit gammas, alpha particles, neutrons, and so on. So you have to shield against those. And in the past, we used what we call passive shielding. So lead is very good as a shield against gamma rays, and polyethylene is very good as a shield against neutrons because it contains lots of hydrogen protons. So these neutrons will slow down, will collide with these protons. And then for Xenon 100, we improve this quite a bit. We also added an inner copper shield. So copper is one of the cleanest materials that you can produce. And we also removed, all of these extra components here, cables to outside of this shield. So here we had actually a factor more than 10 improvement in backgrounds. But on the other hand, these sort of passive shields are not convenient anymore when you go to these much larger detectors. So when we went to Xenon 1 ton and now here to Xenon N ton, we added here, I will show you more pictures, actually a 10 meters by 10 meter water shield around this cryostat to reduce even more this background coming from the walls of your laboratory. And here we then added inside of this water shield an additional shield that is reducing the flux of the neutrons that can give you signals that look very much like the ones from dark matter particles. And we will come back to this, but also to mention yet another necessary step that we have to do that takes many, many years. So apart from reducing, so in this case, we reduce the background that comes from the outside, from the lab, okay? However, also your detector materials, they will not be absolutely what we call radio pure. So they will still contain small traces of uranium and thorium, of potassium, maybe of cobalt-60. So we have these extra germanium detectors that we also operate deep underground that we use then to measure the radioactivity and also select all of the materials that we later use to build the dark matter detectors. And that actually takes many years. This is just one example here, but for all the materials, we have to measure how much uranium, how much thorium it contains, and so on. And then we have to decide, is this material good enough for building the detector or not? And we know this because we do Monte Carlo simulations of the geometry of these detectors and of the radioactivity of the materials that then can tell us how much background to expect, how much background events to expect when we start taking data. So actually, this is how the xenon 1-ton experiment and similarly n-ton looked like in Gran Sasso. So you can see here only this large water tank from the outside. And because we cannot see inside, we put this picture of the detector, how it looks like. So we have this so-called cryostat and the liquid xenon detector. I will show you it's inside. So again, this cryostat helps to keep the liquid xenon cold, to purify it. So we have this... we transport here the liquid to up to this room, what we call the cryogenics room. Then we have here the data acquisition room, all of the electronics, where we also acquire all the signals. And then here we have this large storage vessel. So when this xenon is not inside a detector, you have to store it somewhere. And we call this rest stocks. So we can then store the xenon in here. So this is this building. You see here some people. So it's also about 10 meter high. So the detector is inside here. And this is what we call the service building. That is, of course, also very important. Now, if you go inside of the water tank and before we fill the water, you can see here the cryostat. So the detector, the xenon detector is inside this cryostat, but also the water shield is not just passive, but it's actually active in the sense that it's also a detector. So we have all of these photomultiplier tubes. Some of them you may be able to see. And when, even though we are deep underground, there are still some particles from cosmic rays that can penetrate, and those are muons. So they're like electrons, but much heavier, about 206 times heavier. And so they don't lose so much energy, and they can penetrate deep underground. Even though in Gran Sasso, the flux of these muons is reduced by a factor of 1 million, we still need to shield against them. So we have this what we call Cherenkov water shield. So when these muons pass through here, then there is a signal that can be detected in the water, and if we have a signal here in this water when it's there, together with a signal in the liquid xenon detector, then we know this was not a dark matter particle. Why? Because the fact that the probability that they interact twice in the water and in the xenon is very, very low for dark matter particles. It's almost zero. So we reject those events as being due to background, for instance, due to muons. So this is then when we first started to build the inner detector, that what we call a time projection chamber. You see here very nicely all of these copper rings, and we need those because what I mentioned, we also need to apply an electric field in order to drift this electron upwards, and this electric field has to be very uniform. So that's why we have all of these copper electrodes. And then on top and the bottom we have PMTs. So this was an image that when with some students here, some PhD students, we were putting together the array for these PMTs that I will show you, that a few years ago actually made it to Le Monde. So this is when we were building this xenon 1-ton detector. And then once everything is ready, we actually install it again in a clean room already at the Gran Sasso laboratory, and then we will bring it underground. Okay, and this is how it looked like in the clean room. And here you see a little bit better these what we call photosensor arrays. So these are photomultiplier tubes. They are very special detectors because they have, first of all, they have quartz windows, so they can detect the UV light. Normal glass would absorb this, and also they have very high gain, so they amplify a signal by a factor of roughly 5 millions. So we can see single photons, single particles of light with these detectors, and also they have very low radioactivity. So we developed this together with a company, Hamamatsu, in Japan. And these we also call the eyes of our detectors, because these, yes, they observe the signals. Now, I will not go through, so Xenon 1-ton a few years already stopped taking data, and we didn't find the dark matter so far. So even if you don't find anything, what you do then is to get so-called exclusion or limits, upper limits. So this is the interaction cross-section, the probability that the dark matter particle will interact with, in this case, a nucleon, a proton or a neutron in your xenon as a function of the mass. And if you haven't seen any dark matter particles so far, then so this is these are the results from Xenon 1-ton. That means all of this parameter space that is theoretically possible is excluded. And you can see here also constraints from many other experiments. So basically all of this region is already excluded, but we want to probe this remaining region also here at lower dark matter masses until this blue, you see here the blue region, and that will be the case once neutrinos will actually be our main background, which is interesting because they will also be a nice signal, although not a dark matter signal. Neutrinos are particles, so in this case, neutrinos emitted from the sun, or here neutrinos that are produced in cosmic ray interactions. And because they also have these very weak interactions, neutrinos will penetrate deep underground, so there is no underground lab that actually can shield the neutrinos. So at some point we reach here these regions where neutrinos will be the dominant background. However, with Xenon 1-ton, we did other observations, but one I mentioned here is a very, very rare, actually the rarest decay process that was ever measured in the universe, the so-called double electron capture in 124 xenon. So our xenon contains different kinds of xenon isotopes that are all stable, and in this case, 2 electrons from the shell are captured, and you produce 124 tellurium and 2 neutrinos, and the neutrinos will simply escape. You will not see them, but you will see some X-rays because that will be emitted when the atom gets de-excited, right? And we did see this X-rays. So these were some early measurements. Now actually the signal in the end was even stronger. And because this has such a long, as I mentioned, the longest process ever measured, with a half-life of 1.8 times 10 to the 22 years, so very, very high, this was actually also featured here in Nature. And you can see here again the detector, the cryostat. However, we mainly want to detect dark matter, and we didn't find it yet. So we had to build the next experiment that looked very similar, the INSPYRE, however, a much larger mass. So from 3.2 tons in total, now 8.6 tons of xenon. And this is all new, so it looks very similar, but it's larger. We also have this new array of photosensors. So we had 248 in xenon 1-ton. Now we have almost 500. And we also have this new neutron shield that surrounds the cryostat, inside the water. So you can see parts of it here. So this new experiment actually started in last year, and we are currently taking data. And we hope to have results here on the dark matter search sometime this summer. So stay tuned. But at the same time, as soon as you take data with one experiment, you already start to consider the next one, because perhaps the sensitivity here is not high enough to actually discover dark matter particles. We hope, of course, to discover them, but even in that case, we will only see with this experiment a handful of events. We know this because we haven't seen these dark matter particles with the previous generation of detectors. But to learn much more, so once you discover them, you want to know, okay, what is their mass, perhaps what is their spin, and so on. So you want to learn much more about these particles, so you need a larger detector, higher statistics. And that's why we already do a lot of R&D for this future generation of detectors. And before we come to that, I should also mention that these kind of experiments are not conducted by a few groups, by individual groups, but by international collaborations. And in this case here, we are about 181 scientists from 27 institutions from 12 countries around the world. And you see here one of the latest pictures that we had. It was not a Zoom picture from our meeting in Gran Sasso. I think this was in September of 2019. And soon enough, we will meet again in person, again in Gran Sasso. So this Glennon collaboration, together with additional groups, they formed the so-called Darwin collaboration. So an even larger collaboration that wants to build what we call the Darwin Observatory. So this ultimate dark matter detector that wants to probe all of this region until we hit what we call the neutrino floor or the neutrino fog. So this region where the background starts to get dominated by neutrinos. So again, you see this geometry is very similar to this previous generation of detectors, but there's still many technical challenges that we need to overcome. And because of this, I will not mention here, there are many other kinds of physics that we want to do, but I will mention some of the technical challenges that we want to address. And because of this, we need to build so-called demonstrators. And here in Zurich, in our lab, we have one of the demonstrators that is sort of building like one slice of the detector here in Z dimension. So you have the final dimension in Z. So the TPC, this time projection chamber, has 2.6 meter in height. And we want to demonstrate, for example, that we can really drift these electrons over this distance. It is always a challenge to detect a few electrons that are produced here and to drift them all of this distance, because they get absorbed by some impurities that are remaining in the xenon. So this is one challenge that we want to demonstrate. Another one is perhaps to go to other type of photosensors, for instance, the so-called silicon photomultipliers. These are much smaller silicon-based devices, and they would give us a much better, for instance, position resolution. And this we study first with the smaller detectors, so one that we call Zurich here, and then we will have an array of these new type of photosensors in this larger detector. And as I mentioned, in Xenon, but also in Darwin, we have many different institutions. So we conduct R&D not only here in Zurich, so this is the example, but in many other places. So for instance, colleagues of mine in Freiburg, they have a demonstrator that is very flat, but that in XY has already the final dimension of the Darwin detectors, for example, to check whether you can build these electrodes, so the cathode, the grids, the anode, that have such large diameters and that are still stable, and they don't break, they don't sag, and so on. So apart from these technological challenges, and of course putting together, building this new detector, there's still many open questions that we need to address. Right. So first of all, we need to discover these dark matter particles, and to answer the question, is dark matter really made of these new weakly interacting massive particles? And once this question is answered, hopefully, then as I already mentioned, we want to know, okay, what are the detailed properties of these particles? What is their interaction cross-section? What is their mass? And then maybe there's more than one type of dark matter particle. So the simplest hypothesis, it's one, but we know that this visible world, these other particles, we have many different types. And maybe maybe there is a so-called dark sector out there with more than one type of dark matter particles. So we are looking also for others, other candidates, not only these weakly interacting massive particles. And later, you have seen that our signal depends also on the density of these particles in the Milky Way and or their velocity distribution. Now, once you measure something, you can also hope to find out something about their velocity distribution, about their density. So the other way around, and the hope is that we have at some point a much more detailed study of the dark matter distribution in the Milky Way, but especially also in the solar system. So there's all these questions to be answered by future generations, of course, of scientists, of physicists. And yes, I will stop here, and I look forward to your questions.
Thank you, Professor Baudis, for this very interesting webinar. It was really, really interesting and beautiful. We have a question. How we know something that is dark?
Right. So how do we know? Yes. So how can we detect something that is dark? Right.
Yes.
Is this a question? Yes.
Yes.
Yes. So in our case, as I said, dark means simply that it does not emit light or it does not scatter with light, but it can still have other type of interactions like this so-called weak interaction. So it can still scatter of an atomic, of a nucleus or of an electron without emitting any light, but it just transfers some energy onto other particles that we can then see, right? That interact then with the material in your detector. Now there are other ways. For instance, at accelerators like at CERN, you can also what they do, they smash protons together and they produce many other particles, and the hope is there that amongst these particles they also produce, for instance, dark matter particles. And again, then they see all these particles by the tracks that they leave in the detectors that surround this interaction, these collision points, and the dark matter particles, they will simply fly away. But by measuring all the other particles, they will know that some energy and some momentum is missing. And this is how they know that there was a particle there that is actually dark. And this is very similar to neutrinos. So we can detect neutrinos. It's very, very hard to detect them. Neutrinos are a bit like dark matter particles, but they are very, very light. But they also do not really interact with light, right? So, however, they can transfer energy onto electrons. They can transfer energy onto atomic nuclei, for example. And this is how we detect neutrinos that are emitted, for example, by the sun and by other sources. So it's a bit similar, only that we imagine that these dark matter particles are much more massive than neutrinos. Neutrinos are very, very light, much lighter even than electrons. However, we don't know their actual mass. Yeah. So I hope I answered the question.
Yes. So another question: in case dark matter particles will be discovered, will they be part of the standard model, or will they belong to a new, different model?
Yes, that's a very good question. Yes. So exactly. So actually, the standard model does not predict these dark matter particles. So there are many new models that are so-called extension of the standard models, and these new models they predict actually dark matter particles, like for instance so-called supersymmetric models or some models that are that predict large extra dimensions of space and so on. So if these particles are discovered, they're indeed they will be part of a new theory that's what we call beyond standard model. And some of these beyond standard model theories, they predict many new particles, and the lightest of these is usually the dark matter particles. But some other theories, they only predict very few. There could be some so-called minimal extensions to the standard model, where you have maybe, I don't know, maybe one or maybe only three new particles, and one of these is the dark matter particles. So unfortunately, yes, there are many theories, and I didn't talk about this here, but that also means that there's no detailed prediction of what we expect in terms of this interaction strength that I showed on the y-axis, and in terms of the mass of the particle. If the theory would tell us, okay, this is the mass and this is the interaction cross-section, it will also be much easier to build experiment. But because the theory predicts quite a range, so particle mass is what I've shown here is from, let's say, 1 times the mass of the proton up to 1,000 or even higher times the mass of the proton. But there are other theories that predict even much lighter particles that could be the dark matter. So really the predictions are, they span this very large range. And this is why it's also so challenging for experiments, because we need to cover these large ranges in terms of mass of the dark matter particle, but also in terms of the interaction cross-section. Yeah.
Can you repeat which is xenon's role in dark particles detection?
Yes, so xenon, exactly. I would say that for particle masses that are from, let's say, about 5 times the mass of the protons up to pretty high masses, xenon has now, these xenon detectors have now the best sensitivity in the world in the search for these dark matter particles. And so speaking now of this xenon n-ton detector that has about, as I said, 8.6 tons of liquid xenon, there's also another one that I didn't mention that is in the US that's called LZ, Lux Zeppelin, and they also take data at the same time. They have 10 tons of xenon. So these xenon-based detectors have now, yes, the highest sensitivity for this kind of dark matter particles, what we said are what are called weakly interacting massive particles. And of course, it's very exciting because now we have new data. And what I also didn't say, we don't, in the region where we expect the dark matter particles to interact, so in a sort of parameter region, we don't look in that. So we do what in physics is called a blind analysis. So we look in other energy spaces and so on. But we have what we call the box that we open at the end when most of the analysis parameters are fixed, and then we open the box because we don't want to bias ourselves in this analysis process. So then we open the box, so virtually speaking, and we see whether we found some dark matter particle candidates or not. And in our case, with this xenon n-ton detector, that will happen in the next few months. Yes.
One question again. How does gravity generated by the dark matter's mass influence stars and galaxies?
Yes, that's a very good question. So there's in galaxies, like in the solar system or so, let's say, the density of dark matter is much lower, many orders of magnitude lower than the density of the visible matter. However, because the dark matter, this is how we picture it, is much more extended on the scales of galaxies than these luminous parts, the total mass of the dark matter is much higher. And so you can imagine that this dark matter provides this stability. So the gravitational force that comes due to this entire mass of these dark matter particles that extend far outer than the visible parts. So they kind of stabilize, if you want, the motion of stars, of gas in galaxies, right? And how do we study this? So for instance, we study exactly, so not we, but astronomers, astrophysicists, they study exactly the motion of stars or other objects in the solar system, for instance, with data that are now coming from this the so-called Gaia satellite, where you study the three-dimensional motion, and there you see how much comes, you can disentangle a bit how much comes from the influence of the luminous matter from other stars and gas, and how much comes from these dark matter components. how much of this motion. And this is it's very difficult to study actually. Yeah, so it's important that this gravitational influence of dark matter on stars and on all the other objects is important, but locally in the solar system, it's very hard to study, because here, of course, we are totally dominated by the luminous matter.
So another question, what is the spin of the particles of dark matter?
Yes, that's so this is something that we would try to find out indeed, and we don't know. So theoretical predictions, it could have it could have spin 1 or spin 1/2. So spin 1/2 particles are also called spin half particles are called fermions, while integer spin, like spin 1 particles, like the photon, are called bosons. And depending on the theoretical prediction, there are different possibilities actually for the dark matter particle. And it's a very good question, because it's something that with xenon detectors we might be able to find out. Because if they have spin, they could also have like spin 0. For instance, the Higgs boson is a so-called scalar particle, has spin 0. But if they have spin, then they interact a bit differently with some of the xenon nuclei. So there's also nuclear spin, a total angular momentum of the nucleus, and there are 2 xenon isotopes that have a spin. So that is 129 xenon and 131 xenon. And together these make about half of all the xenon isotopes in our detector. So it's something that I didn't mention here, but yes, we are also looking for interactions between a possible spin of a dark matter particle and the spin of these nuclei. So the short answer is we don't know yet, but it's something that we want to find out what the spin actually is. Yes.
Is our universe stable?
Well, so far as we see, yes, it looks pretty stable on the so we have one of the questions is, of course, the universe is made of this what we call normal matter, so protons, neutrons, nuclei. So and the question is, are protons stable? And this is something else that other experiments want to measure. But the half-life or the mean lifetime of protons, that is what makes it's the most abundant material, if you want, in the universe at large. So it's protons, hydrogen, helium, and so on. As far as we know, they are stable. Yes. Or at least, in physics, you cannot say they're stable to 100%, but you can say, okay, their lifetime is larger than 10 to the 33 or 34 years. That we know because we have very large experiments like Super Kamiokande and others. They have a very large number of protons, like, around 10 to the 33. So they have many kilotons of detector materials, and they haven't observed any proton decaying yet. And this is how you can in principle measure such a very long lifetime that is many, many, many orders of magnitude larger than the age of our universe.
So one last question, is dark matter related in any way to dark energy?
Not really. Yes. So dark energy, it's a very good question. Dark energy is another big unknown. So dark energy is mostly it's a property of space, and it's very uniform. It's very uniformly distributed, right? For instance, it could be, we don't really know whether it's constant in time or not, but it could be constant in time. So far, this is how it looks like. So it could be something like a cosmological constant but it's something that is uniform and does not form structure, does not form galaxies and galaxy clusters and so on. And that's very different than dark matter. That and also dark energy has a different property, namely it actually drives it accelerates the expansion of the universe, right? While dark matter, because of the force, because of the gravitational force that it has interaction, it actually would slow down, and it clumps, it forms the structures that we see today. So they don't really have a priori anything to do with one another. Yes. I would say dark energy is even more, you could say that it's even more exotic, while but it's much more difficult in the end to characterize than the dark matter, in case we really discover these new particles.
Last question, very last question. How do dark matter particles react with their opposite light particles?
So maybe the question is, how do they interact with antiparticles?
I guess it's light with light.
With light. How they interact with light. Yes. So as far as we know so far, if they have any interaction with light, that it must be very, very small, below the strength that we can measure so far, right? So as far as we know, they don't interact with light. But again, in physics, you cannot say this to 100%. You can only say up to a certain point that you can measure. We do not see any interaction of this dark matter with light. So they don't emit any photons, or they also do not absorb any photons, these dark matter particles, in contrast, of course, to other particles that we know. Yeah.
Okay, so thank you again, Professor Baudis, for this very, very interesting talk. Thank you to our students. And let's meet at 4:30 for the second talk. Please wait on this playlist for the second webinar. So talk to you later. Bye-bye.
Thank you very much also for the good questions.
Yeah,
And
very good.